Welcome to podcast episode number 26 of the ISBC Tailboard Talks podcast. I'm your host, Mark, and along with me today again is our special guest, Mr. Jim Vaughn, and we'll get to Jim just here in a minute. This is also episode number 4 of our 5-part series on EPZ and field safety with Jim. And so today's episode is EPZ and substations. To date, we've covered the laws and principles of EPZ. We've covered distribution and URD, and we've covered transmission and induction. So if you've missed those first 3 episodes, I would highly recommend you go back and take a listen there. This is kind of a building block process. I would say at a minimum, you at least want to go back and listen to the first episode in the series on the laws and principles. That'll kind of set the stage for you in listening to the rest. And if you do have questions, they can be sent to podcast@ispconline.com. I know in a couple of the other episodes, I also gave my email address, mark@ispconline.com. So either way, your questions will come to us. And if we have enough questions, we may entertain a question and answer episode to follow up this series. If not, we just got a couple, we'll make sure we get them answered as well. Today's podcast is sponsored by Bierer Meters. Bierer Meters is a family-owned and operated, made in the USA since 1987. Bierer produces the absolute highest quality of lineman-proven, safe, dependable, accurate voltage and phasing meters, secondary testers, cable identification tools, grounds testers, high pot tools, custom temporary protective grounds, jumpers, and pole guards. BiereMeters.com. You can also reach them at customer_service@BiereMeters.com. Lastly, by phone at 803-786-4839. Again, that is Bierer Meters. Great family-owned company there. Do a lot of support for our industry, and we'll talk about that more as we go through the episode. A great partner of ISPC, and we thank them for everything that they do for us. All right. Again, today our guest is Jim Vaughn, senior consultant for the Institute for Safety and Powerline Construction, and an industry expert in grounding and bonding. Great to be back again, Jim, for another episode.
Yeah, thank you, Mark, and thank you for making this time available for us, too.
No worries. I think by now, we can probably skip by the tell us who you are. I think everybody knows who Jim is, and for sure, if they've listened to the episodes, we've detailed that. Probably just the way we've done the first 3 episodes. Again, we're here to talk about the equipotential zone, and I think we've detailed the evolution of the EPZ and the fact that it's basically been around for sure since OSHA instituted grounding policies back in the mid-70s. There's been a little bit of greater detail added to that paragraph in specifically stating that we're required to establish an equipotential zone. And, for those that don't know, 269N3 tells us that we have to place our temporary protective grounds at such locations and arrange them in such a manner that the employer can demonstrate will prevent each employee from being exposed to hazardous differences in electrical potential. And so it's been around forever. I think we'll probably detail again today in this episode, the fact that there is a lot of folks out there that are still not complying with this regulation for one reason or another. Some, in my opinion, because they choose not to. Some, I don't think, understand, fully what they're not doing, or maybe what they think they're doing. And when you really sit down and look at it and talk about it, they're like, oh, I didn't really look at it that way. I guess to start off, Jim, in our tailboard topic, before we jump into the meat of this thing, as I've done in the past couple episodes, I think we've detailed all the way from episode 1 what OSHA expects. What's different when we step inside that chain link fence, right? And so we've talked about overhead, underground, and transmission, and so on. But people, especially linemen, tend to get a little uneasy when they step inside that chain link fence. And what changes? What's the big deal? Most of us, especially I'm from the substation world. I kind of feel protected inside that substation fence. But for a lot of other folks who are like, no way, man, I'm staying out of there. I don't want anything to do with that substation. So what's the big deal?
Yeah, sometimes it's knowledge. I use an example. If I get in a room full of 25 linemen and or substation techs or anybody else, there's going to be a number of them that had military service. I make this observation. If I was to grab a grenade out of my pocket and hold it up in the room, everybody that's had military service and been trained on grenades, and especially if they had combat service and used grenades, they're not going to be too upset.
Mm-hmm.
Everybody else is going to take them to figure out a minute of what it is, and then everybody's going to get really excited, about it, because it has to do with, your experience and your knowledge and your training. And that's one of the things that's missing
Mm-hmm.
in the substation world. I just answered a question on this, and by the way, Incident Prevention Magazine, if you don't get it. It's free. If you're in the trade, you can get it for free, or you can go online and you can see the articles that are in there. And in the most recent edition, I was in a bad mood and I wrote a pretty aggressive article on equipotential grounding. EPZ, it's the law.
Mm-hmm.
And what stimulated me to do that is yet another case showed up and most of you know that I do the litigation support for ISPC. I got another case where a journeyman worker was killed by the grounding that they installed for his protection. And there's no excuse for that, because we're supposed to know how to protect ourselves and what grounding is for. So we're talking about knowledge, and we're going to be talking about knowledge about how substations work and how they protect you. And really, as far as getting electrocuted, substations are the safest place to be within the whole system from generation all the way to a meter base, because the substation is a big EPZ plane. It's a great big ground mat. It's just like the one that you roll out next to your truck and stand on to keep from getting electrocuted. And that's exactly how a substation is built. But that doesn't excuse not training everybody who's going to walk inside that fence, because there's a reason for that fence. And the reason is because there are things in a substation that will kill you.
Yep.
And everybody that needs to go in a substation needs to have substation entry training.
Mm-hmm.
Now, ISPC does audits of utilities, practice, procedures, and policies, and Mark does those same audits. And we go to a client utility and we'll go and do an inspection or an audit of a substation, and we'll find some pretty big holes in their substation practices and policies. And the reason I was thinking of IP is because I think it was the last edition or the one before that that I answered a question that kind of ticked off some engineers, because this guy had a concern that their classically trained electrical engineers were walking into a substation and did not have substation entry training, and he saw them doing things that are recognized as hazardous. He's absolutely right. Just because you're an engineer or just because you're a journeyman lineman doesn't mean you're qualified to walk into a substation. And everybody needs to have substation entry training to make sure they know what's going on when they walk inside that fence, because a substation requires you to have a 360-degree awareness. When you're walking towards a bus, when you're walking towards a piece of equipment, you need to learn how to visually scan that equipment and recognize deficiencies. Because even though I said that a substation is about the safest place to be when a fault occurs, sometimes the equipment blows up, and that's not the same thing.
Yeah.
When that happens, because when stuff blows up inside of a substation, some areas are better protected than others, and you can have some mighty powerful fault currents go off. And I know of a CT that shouldn't have been a window CT anyway in a substation, but they had one on a bus that went between the transmission provider and the distribution system for a municipal utility, and they used window type CTs, and the CT failed. And there are four, um, uh, I think there are about 5/16 bolts that go through that hold the CT together, and one of them erupted under the force, the magnitude of the fault current, and
Mm-hmm.
punctured a regulator. Now, they knew they lost the metering, but they didn't know why. And then when they had to go because the regulator exploded, when they got in there and they found a hole in the side of it, first they thought somebody shot it. When they untanked it, they found a CT bolt,
Mm.
inside of it. So, equipment can blow up. So that's the very first thing that we need to recognize. Now, that just means, too, that if you're going in a substation and you're grounding in that substation, if you don't have this basic awareness about how the substation grounding system functions, you might be setting yourself up.
Yeah. Yeah.
So the next thing that I want to make sure that we understand is the difference between grounding and bonding. And then I want to cover a few of the things that we find in substations that really limit the nature of the protection that we think that we're installing inside of a substation. So, first thing, grounding is protection of the circuit. It's there to trip circuits and protect the equipment from exploding fault currents and all the kind of damage that it can do. That's the purpose of grounding. The purpose of grounding is not to protect workers in the substation, even though it does have an effect. And we're going to talk about that in a minute, because it's what we call an incidental level of protection for the worker
Yeah.
that's created by the multi-grounded system. Bonding, on the other hand, is to protect the worker. So grounding is to protect the substation, bonding protects the worker. This is a point of knowledge that everybody needs to have so that we can evaluate the personal protective grounding that we install for our protection. Now, that also needs a little bit of explanation. When OSHA mentions personal protective grounding, they assume that everybody understands that that personal protective grounding complies with that N3 standard that you read earlier, that ground
Mm-hmm.
shall be placed and arranged in such a manner to ensure that the employee is not exposed to a difference of potential. So when OSHA says personal protective grounding, they mean EPZ grounding. EPZ
Mm-hmm.
grounding is the law. So that's where we get them mixed up, and that's the reason why I really kind of like to, stick with, especially when and this happens all the time. And Mark, I know you see it too. When we go and we do grounding training for utilities or contractors, it's a lot of information that has to be delivered in a very short amount of time, and it's pretty easy to get confused. And we'll have a question that'll come out, and you can immediately see that, oops, they're mixing up grounding and bonding. So the first thing you have to say is, okay, now remember, grounding is for tripping circuits. Bonding is for protecting the worker. So what we're talking about here is that bonding.
Just wanted to give another shout out to our sponsor. Bierer USA Utility Support Assistance is Bieer's one of a kind, no cost service to the electric utility industry, including professional customer service, technical support, repairs, and calibration, live line conferencing, on site field training, and speaking at tool and work methods committee meetings, safety conferences and seminars, and presentations, and our exclusive 30-day tool trial, beermeters.com. Again, customer_service at beermeters.com or 803-786-4839. Bierer Meters, check them out. You won't be disappointed with their product.
I love those guys. I ran into them the first time about 15 years ago at an IP conference, and I was immediately
Yeah,
impressed with their uh, innovation, their knowledge, and what they were willing to
yeah,
do. And now ISPC, we do a lot of work with Bierer, and the thing is that over the years,
Yep.
as I've known them, I've taken them ideas, and they come out with a tool for it, and they're very willing to work with the industry. In fact, I was with a utility
Hmm.
a client of ours that has concrete substation floors in outdoor substations, and they got to where they said, well, how do, and their substations are 80 years old, and they said, how do we test the grounding system in our in our substation? And we just started thinking out of the box through the principles, and I had a Beer cable, a ground cable tester, and I said, wait a minute, uh, if we connect a row of regulators to a Beer ground cable tester, and we connect one end of the probe and the tester to one end of the lineup and the other end to the other end of the lineup, and we start ramping up the voltage on it. If the grounding system between
Hmm.
the regulators is no good, we'll get a voltage between each regulator. And so we did that, and we went through and we didn't get any voltage. We said it's good. And then I went back to Beer and I said, hey, I repurposed your equipment. Am I in trouble? And they actually took it out in their substation yard and they repurposed their piece of equipment
Yeah.
to see if it was legitimate. And they said, hey, it worked. So it's actually really is the same way that we test grounds, as we put a some sort of a value on it, and using Ohm's law, we use that value to determine what kind of resistance that we're looking at. So
Hmm.
but that brings us to the thing that we need to understand about substations. Everything in a substation is bonded together. The substation itself is a mat. And if you've never seen a substation built, and I've built a number of them, I know Mark has, there's a grid that we bury in dirt that we put in place. And the dirt that we put in place has a known conductivity to it. It's the kind of dirt that we use, and it's a compressible, usually a red dirt or something like that. And we know what the value is. And the electrical conductivity value of the earth where we're building the substation determines how far apart we're going to build a grid, and we're going to bury that grid about 3 or 4 feet deep, depending on what the engineer's design criteria is. So don't take anything that I say as the way to do it, because there is no the way. It depends on where you are, what the conductivity and the mineral content of the earth is, and all the other stuff that goes along with it. But we put a crosshatch grid underneath the substation all the way out to the fence line. And sometimes, if it depends on what utility you work for, some utilities run the grid past the fence, some utilities run the grid to the fence, some utilities stop the grid 5 feet short
Hmm.
of the fence. All three are allowed by the substation grounding standard, which, if you want to double check anything that we say, we base our training and our research that we've done on substation IEEE 80, which is the IEEE standard for substation grounding systems. So we lay out a grid in the substation, and we fill it in, and we backfill that, and then we lay a layer of rock on top of that grid. And this is the conventional substation. And that layer of rock, depending on who builds it and how much money they
Hmm.
want to spend, is anywhere from, I've seen it 6 inches, I've seen it 16 inches. It just depends on what, they decide to build. That layer of rock is actually a buffer. Now, when I first started in the industry, I thought the rock was there to keep the weeds down. I had no idea that it actually had
Hmm.
it was part of a system of protection for the workers in the substation. So imagine, if you will, you are standing over a substation grid, and the grid maybe has 4-aught cables buried 3 feet deep, and they're maybe 10 feet apart. So each one of the grids creates a square, and that outlined by that 4-aught grid that's buried in the ground, because they're all, every place they cross each other, they're either bolted or welded together. So if the substation gets hit by a fault current, everything in the substation is tied to the grid, and the grid is in intimate electrical contact with the earth. And so the grid funnels that fault current into the earth, and the fault current spreads out from each member of the grid toward the other member of the grid opposite it, so that there is a voltage flowing to and from each conductor, and they overlap at some place in the grid. And wherever they overlap, there's going to be a little bit of potential difference between the earth 4 or 5 feet away from whatever that point is. So the buffer layer of rock, and by standard, that buffer, depending on what kind of rock that you use, is about I can't remember now. I think it's 3,000 ohms per cubic foot of rock. I think that's about what it is. So it's there as an insulator. Now the rock itself is not necessarily the insulator. It's the rock itself is a sieve size. The rocks are not round, they're not square, they're all different kinds of shapes, and they have all kinds of air voids in between them, and that helps to increase the resistance of the rock that you're standing on top of. So this is also the place where you need to mention that when you drive a rear axle drive bucket truck through the substation and you bury it in the rock, when you pull it back out, put the rock back. The rock has a purpose to help protect the worker, because what you're doing is you're standing now on a layer of insulation above the grid. Now, current that may be on the substation grid because of a fault does not go up. It goes horizontally and down into the earth. Current has to have a pathway. So this is another fundamental to understand the value of the grid in the substation. Current has to have a pathway. Voltage can transfer an electrical charge from conductive element to conductive element simply by touch. So in the dirt in the substation, if there is a voltage that's associated with the fault current, that voltage can spread horizontally across the substation. The current has to have a completed circuit in order for the current to flow. That completed circuit is through the resistance of the earth to the other members of the grid or down into the earth. So that current flows horizontally and it flows downward, and then you're standing on top of a layer of insulating rock to provide this plane of equipotential for you standing in the substation. And that's good. Everything in that substation, including the columns that equipment is fastened to, or foundations, or pads, or steel columns, everything in the substation is connected to that grid. So if any component or apparatus in the substation has an electrical fault, it is going to send that fault current down into the earth.
I guess another quick point to make, Jim, too, is you mentioned about vehicles, and if you make ruts and things like that, get the stone level back out. If you're excavating in a station too, right, doing some brownfield work or something and digging trenches and or foundations, maybe not so much foundations, but let's say you're trenching across the yard, it's important to put that fill back the way you took it out of there, right? You can't just throw a bunch of 1B or 2B stone in the ditch and say, "Hey, I'm golden," right? You're manipulating the protection that was originally put in there and designed to protect the worker.
And that's a really good point. And that's also the way we explain splicing of underground cable, URD cable. We say maintain the integrity of the cable.
Yep.
Same thing with the substation foundation. The grid that we build in the substation, if we change the density of the dirt, we also change the effectiveness of the grid of the substation.
Mm-hmm.
So it's exactly right. I actually did a case, and I know of a case where a contractor, and shame on them, drove through a substation. They were parking their equipment inside the fence at night, and they had a two-wheel drive truck, and they got stuck, and
Mm-hmm.
they buried the truck trying to get it out. And then when they got it out, they saw the grid. They had actually gotten all the way down to the grid, and they pulled up pieces of copper.
Mm.
And apparently, one of the guys that was with the crew, he's the one who narked on him because he knew that this wasn't right. They said, "I'm not taking responsibility for that." So they took cable cutters to the copper that was sticking up out of the ground, and then came back and shuffled everything back, and they chopped out a chunk of the grid.
Mm.
So I mean, that's one of the things that we also have to be aware of is we can't see what's under the station.
Yeah.
We're looking at rock and everything looks good, and that's good. And by the way, just so you'll know, there's two things that I thought of. One of them you mentioned brownfield. If you're not a substation tech or know a lot about it, we talk about substation work in two different modes. We call them brownfield and greenfield.
Yeah.
Greenfield is where you're looking at the big prairie and there's nothing out there. And when that's called greenfield. And when we go out there, we're going to excavate, we're going to put our own dirt in there, and then we're going to start building our substation foundation, our grounding system. Brownfield is where we go into a substation and we add a bay or
Mm-hmm.
two or more equipment, and we're going to be excavating in the substation, scraping away the rock, finding the edge of the grid and attaching to the grid and stuff like that. So that's the difference between the two. And brownfield can have some risks associated with it because we are talking about attaching to the mat that we
Mm-hmm.
buried in the ground on an operating substation, and we'll probably get to that back later on today because right now I want to stay with the theme that that we're working on about the design of the substation and everything being attached or connected together or bonded together. So, I was mentioning about the fact that we can't see the condition of the grid. Now,
Mm-hmm.
when substations were first being built, nobody was really trying to build in a way to test the effectiveness of the substation grids. And now, substations that are being built, and as a contractor building substations, we do on occasion put in test wells where
Mm-hmm.
we can actually get into the system, and you can do a fall of potential test using Biddle measures or something like that. And when we built the substation, we took a baseline test at each one of those wells. That information becomes the baseline for the integrity of the substation system, and then every 6 months or every year, the utility comes back and they do those same tests with the same kind of equipment and in the same way, and they measure the continuing integrity of that ground system. If you own a substation and everything's going along fine for 20 years, and then all of a sudden you start blowing arresters and having equipment failures and stuff like that, that usually is telling you that beside the fact that if you know you didn't get struck by lightning, your substation grid is probably in need of repair.
Mm-hmm.
Because if the grid is not working right, then neither does the protection. If the protection doesn't work right, then the people in the substation may be at some measure of risk also. So we have a rule in substations that says when you approach apparatus in a substation like a circuit breaker or a regulator or a transformer, you visually ensure that the ground connections are in place. And if you don't see those ground connections in place, you handle that piece of equipment or apparatus with gloves until you ensure that the equipment is properly grounded for your protection. Because if you're standing over a grid that is at one potential and you're touching a piece of equipment that is not bonded to the grid at a different potential, you don't have any protection
Mm-hmm.
from that piece of equipment. If you see that 2-aught or 4-aught ground cable going down into the earth, we make the assumption that it is connected. Now, when we have manual switches in a substation, in most cases, the engineers will include a switching mat, usually constructed of galvanized steel. It's usually just the right size so that when you complete the handle throw, you step off of the mat. That's a joke because it actually really does seem to do that sometimes. But standing on that mat, that is the opposite of incidental protection. That's called intentional protection. The mat that you're standing on is usually made out of a galvanized grid welded together and regalvanized, and then it'll be bolted to the column to the that 4-aught cable that's coming down the column going down into the grid connection below the substation. The idea is that if something should happen, everything is going to be at the same potential. So this is another one of those important things that you need to know. Now, we all know this because if I ask the question, what is it that will kill you with electricity? Is it the current or the voltage? Everybody that's listening would say, well, it's current. Yes, it is. Well, sometimes we get that confused in our discussions. Remember what we said about current. When current flows across the substation, gets on one of those ground cables and goes down into the earth, that current cannot come back up. It goes horizontally or it goes down. That's just the physics of electricity because current has to have a path. It's like what we talked about in transmission. We may have induction on the pole being collected by the pole bond going down into the earth, but that induction current going into the earth is flowing all the way to the next structure, creating a circular pathway and circulating current within that pathway. And that's just the physics of current. That's exactly the way it happens in a substation. Voltage, on the other hand, will not do that. Now, this is good knowledge because if you look in the standard, the substation standard 80, they have permissible voltages that could be exposed to a substation worker in the case of a fault. And you look at those permissible voltages and you see that thing says 2100 volts. And you say, well, that's not very safe, but that's voltage without a current component. No AC current, it's just voltage. Voltage without current will not kill you. Whatever caused it, you don't want to do again, and you'll remember it, and you'll never, I'm not doing that again, but it won't kill you. Mm-hmm. So bonding is to keep that voltage low. In other words, sometimes in the OSHA standard, it says below the level of hazard. We use universally, accepted in the industry, as 50 volts. 50 volts as being the level of hazard. And that comes from Dalziel's old work where how much voltage does it take to penetrate your skin? Even though he was researching the damage that current can do to the human body, but he noticed that it took different voltages to break the resistance of human skin. And we have said that's 50 volts. Okay, that's a buffer that's built into our systems that also has made us maybe a little skeptical that there is a risk sometimes because these voltages occur all throughout a substation, every place there's connection, just like out on a distribution circuit or a transmission circuit. Everybody knows what happens if I bolt a number 4 aluminum onto a number 2 aluminum with an A to A connector, and that connector goes bad. What's going to happen? A resistance is going to form, and a voltage is going to appear across that connector. So that brings us back to those original rules or principles that we talked about from the very beginning that is worthwhile mentioning here because it also has to do with the safety of grounding in a substation. And the first one is that current follows every available path proportional to the resistance of the path. So that means every available path, every column, every apparatus, every foundation, every buried column foundation that's in a substation, all of it is steel reinforced and all of it's grounded to the substation grid. And we use pretty big cables to do it with pretty reliable connectors, and substation maintenance people go in and check those connections all the time, looking for the appearance of heat, or they thermally check them. They'll put a voltmeter on them to see if there's any voltage across there because they're testing the integrity of the system. Our multi-grounded system, incidentally, helps to ensure protection of the worker. But that's also part of the reason why our grounding system in a substation can become deadly. See, in your house, every 3-prong plug that you have has a little round pin connector in the United States, and that's a ground lead. And that ground lead is isolated from the neutral and the hot leg all the way back to the circuit breaker panel, or what they call the first means of disconnect. So that ground is isolated. It will never have any current flowing on it unless there's some appliance failure in the house on that electrical system. Well, in our systems, in our substations, everything is connected together. Every distribution neutral is bonded to the substation ground grid. So our first rule is that current flows in every available path inversely proportional to the resistance of the path. That means that on the power transformer, if I bond that neutral to the tank of the transformer, that some of that neutral current that's returning on the distribution system is staying in the coils of that transformer through that neutral connection, but some of it is also flowing down that ground connection into the earth. And that's the case with if I've got potheads leaving the substation and I've got concentrics that are twisted up, they're bonded to the substation steel. Even though they're all tied together and the three of them work together as a neutral system for that distribution circuit, part of that current is going into the substation steel, into the substation ground. So if I interrupt any of those pathways, it's the exact same thing as cutting a system neutral out on a distribution circuit. And nobody in a substation or out on a power line is going to cut the ground connection on a cable and get between them barehand. If you did, you would probably get killed. But that same theory of risk and protection exists with all of those grounds inside that substation. I'm always amazed. When I first started studying this 20, 25 years ago, I had no idea, what these risks were. And so I couldn't figure it out, but I wasn't satisfied just to say, I started doing the research. And one of the things that I did is every time I went in a substation, I took a clamp amp meter with me and I started taking pictures of current on transformers and current on steel. And every time I would clamp a ground, I would find current flow. And, most of the time it would only be 4, 5, 6, 7, 8, 10 amps. But on power transformers, it would be 40 amps. Every one of them has current flowing on them. And we haven't been teaching people that. And when we go and we do substation grounding, I show those pictures and I see a whole bunch of substation techs going, "Ooh, had no idea." And I had a lot of fun one time, spent a whole week at a utility. And so every 2 days we were going out into the substation for a practical look at grounding. And the 20 techs that would show up every time, every one of them came out with a BOM. And the first thing they did was walked out and started checking grounds to see what kind of current was flowing, because they didn't have any idea that it was there. But, you look at it and you say, oh, that's just a ground. But if it's a ground on a power transformer and you unbolt it and you got your left hand on the bare cable and your right hand on the pad on that transformer, it'll kill you. Now, you're not going to get system voltage. And that's what we always say when we teach apprentices or apprentice techs. We say with a system neutral, if you were to open the system neutral, you could have system voltage in that open. And that's true, which would be the worst case event. You would have system voltage. You're not going to have system voltage if you open a ground on a substation power transformer. And the reason is because the one that you're standing at probably has a duplicate to it someplace else on that transformer somewhere else that is carrying part of that circuit. So if I unbolt the one pad, instantaneously that current is going to be on the other pad, 20 feet down away from me, but that pathway on that other connection is acting as a bonding jumper across the gap that I just made. Now, that's not intentional protection. Intentional protection is, and I don't know any reason why anybody would do this, but if I was going to unbolt a full rod ground on a transformer in a substation, I'm not going. I'm going to mac it out first before I lift that off of there. Now, anytime we go into a substation, an operating substation, and we make a
Mhm.
ground connection, especially if you're doing it in the dark, when you touch those cables together in a connector, you see a little spark. It's always there. That spark is a message. That means that there's current available on that circuit. So, how come, as I said earlier, even if I cut a system neutral and pull it apart, I'm not going to get 7,200 volts? If I'm on a 345 kV power transformer and I lift the ground lead on that transformer, I'm not going to get 345 kV, on it. And the reason is because of the multi-grounded system. That multi-grounded system means that the one that I take apart, next to me, in front of me, behind me, everywhere else, there's another ground cable coming down somewhere, coming down somewhere, coming down somewhere. And every one of them are acting as a bonding jumper across the gap that I just made, keeping the voltage in that open very low. That's the buffer that we talk about. Remember, leading into this part of the discussion, I said 50 volts. As long as the voltage cannot break the resistance of your skin, current can't flow. And if current can't flow, you can't get hurt. You might get shocked when that voltage breaks the resistance of your skin. That opens up a pathway allowing current to flow. But if that voltage is not high enough to break the resistance of your skin, then you're not going to get shocked. Current's not going to flow, and you may come away with a lack of respect for the hazard that's actually there. We don't want to open up these circuits, and that's the same thing when we're grounding inside of a substation. And there's two important things about grounding, and we have a thing that we call it the cardinal rules of grounding, and there really is no such thing, but this is a way to emphasize how important these things are. So, a cardinal rule is a rule you can't live without. And that's a very good way of saying it because if you violate these cardinal rules in grounding, they'll get you killed. So, one of the cardinal rules is that you make your connections with a hot stick. And making your connection with a hot stick means that you're not going to be there hands on making a connection on a grounding system in a substation that may be subject to an unexpected and instantaneous fault current. You have no idea when it could happen or when it could occur. So, the basic rule in a substation about columns and apparatus is that's not where I'm going to eat my lunch. If I'm working in an operating substation and there's shade being afforded, by that 25 kV breaker or recloser that is sitting there, I'm not going to sit there, lean up against the frame of the breaker and eat my lunch there. You don't do that. That's just one of those places where an instantaneous
Mhm.
fault could occur. And anybody that works in substations will tell you a story of being in a substation and hearing that wee, of that recloser reloading after a fault occurred, and you had no idea it was coming, and it's a big surprise. And substation professionals, when that happens, everybody stops, and looks around and says, "What's going to happen next? Is it going to happen again?" And most of them will start heading toward the gate, if it's going to happen again, just because these things can fail. So when we're grounded in a substation, we have to recognize that unlike grounding on distribution, where I opened up a set of switches and I know there's no voltage on the circuit, grounding in a substation can change instantaneously because all of those circuits leaving the substation are usually running parallel on poles or parallel next to something else and crossing under something else. All the neutrals are interconnected. You are at the foundation of that circuit with the highest amount of current that's available in the system is going to be right there. So now, when I'm making grounds in the substation, and this is the last point that I'm going to make, and Mark, if you want to bring anything up that you think we ought to be talking about, I see this a lot when we go and do audits of utilities in their
Okay.
substations. We when we work in a substation, we can bring our crew truck in and drive it right to wherever it is that we're going to work, and that's handy. Um, when we work out in distribution, we can't always do that. And, it would be a pain to have to carry 30 or 40 feet of 4-aught cable for a 4-aught ground that I'm going to hang, on my bus. But when I'm driving a truck, I can carry all the 30-foot long 4-aught grounds that I want. It's easy to get them where I want to be. I frequently see 40 feet of ground to make a 15-foot pathway from a bus bar to a 4-aught down lead or ground lead on the side of a column. I don't think that they realize how dangerous that actually is in two ways. One of them is the voltage that's going to develop across that resistance of that cable is the voltage that you are going to be exposed to if your hands are on that bus and you're standing on top of the transformer or you're standing on the bus rack. See, that ground lead in EPZ is a bonding jumper across your resistance of your body. It's the same thing as an open neutral. I put up a bonding jumper across the neutral that I'm going to open that does two things. One is it maintains the pathway for the neutral current. The other thing is that it makes sure that that voltage in that open does not appear in that gap. You are the gap when you're on the bus. And if I hang a bonding jumper up there or an EPZ arranged ground, that bonding jumper for the EPZ, the voltage across that jumper when the fault occurs, that's the voltage that I'm going to be exposed to. So the whole idea of keeping cables short has two components to it. One of them is the shorter the cable, the lower the voltage will be across the worker. The other is excess cable creates reactive seismic exposure is the way that engineers might describe it. And what it means is that that 40 feet of cable that's laying on the ground is going to whip instantaneously during the first 3 or 4 cycles. You may survive the electrical contact, but if you've ever been whipped by a 4-aught copper, you may not survive the physical damage that it's going to do when it hits you. So keeping them short has really value to it. And this is an opportunity to say one more thing. One of the requirements for grounding for a three-phase system in the OSHA standard is that the three-phase system must be short-circuited. In other words, A to B to C. And then it's grounded in an equipotential manner to provide equipotential protection for the worker. There's a reason why A, B, and C must be short-circuited. If you're a substation tech, look at the wiring diagrams for your three-phase delta transformer. Every coil in that transformer, every winding, A, B, and C, are all connected together end to end, A to B, B to C, C to A. The three-phase current stays circulating within that three-phase system. Now, when we get to the Y side of the transformer, all of those transformers are still connected together, but they're connected together through a common grounded bus called the neutral bus. So A is connected to the neutral bus, B is connected to the neutral bus, C is connected to the neutral bus. The three phases are still connected together, and the three-phase current still circulates within the three-phase system. And where does the current and how much is the current on a system neutral? It's the imbalance of the three-phase current on the three-phase Y transformer. Well, we've said it before, and it still applies. A three-phase fault into a grounded system is electricity. It behaves exactly the same way that electricity does flowing through a transformer, which means that if I short circuit my three-phase bus, A to B, B to C, and if I use cables long enough to make the connections but not excessively long, then the three-phase fault current coming into that system in that connection is going to stay within the three-phase system, and only a portion of that fault current is going to go to ground through the ground connection. And if I limit the current that flows, and this is just like the neutral carrying the imbalance, if I limit the current that flows through that connection, then I also limit the voltage that appears across the resistance of that connection, creating a much more effective level of protection for the worker. If you don't believe what I just told you, and I was surprised to hear it myself, it's in the OSHA standard in the appendix. There's the description of how it works. You'll also find it in engineering books and on three-phase delta and Y and current flow and how current flow works. And you'll see it in the grounding standards for both C2 and in the IEEE grounding standards about the importance of short circuiting the three-phase circuit when you ground that system and making sure that your connections are as long as they need to be, but not excessively long, and that those connections are made good, using the right clamps, using a wire brush, all the things that make that ground connection work.
Before we wrap up, Jim, I think just like we've kind of done with the previous several episodes, kind of that key takeaway, right? So, we've gone over a lot of important things that we have to be aware of inside the fence or in the substation versus out in the distribution world. But what's that one thing that you want people, if they got nothing else out of today, what's that one thing that we need to really be aware of when we're about to step inside that substation fence and perform work in a de-energized, grounded fashion?
It is probably related to the last thing that we talked about, the length of the cables that we work with and the integrity of the system that we install. I see this a lot also, that bracket grounding seems to be the rule in a lot of substation operations, and they'll put brackets up on both ends of the bus. If they do that, they're relying on the incidental protections because of the bonding of everything inside of the substation. We still are required to equipotential bond. So if I'm standing on top of a breaker working on insulator replacement or bus or doing testing, or if I'm on a ladder leaning against the breaker, making connections on to do testing on the breaker or on top of a transformer, and I'm working on the bushings or working on bonding or jumpers or anything like that, that equipotential connection is still integral to my protection because it is intentional protection, not relying on the incidental protections that were built into that substation 20, 30, 40 years ago, and especially on the parts that we can't see. So use what
Right.
you know to protect yourself. I can see the grounding. I can see the connection. Keep the cables the right length, as short as long as they need to be, but not excessively long, and make good connections.
All right. Once again, if you do have questions that you've thought of out of what you heard here today, you can send those questions to podcast@ispconline.com, and we'll make sure and get those answered for you. Electric Culture of Safety is a grassroots nationwide safety partnership bringing the electric utility industry together in unity, building a line team. ECOS partners at no cost to your line crews, sharing their knowledge, experiences, expertise, and passion for the common goal of ensuring our heroes of light return home safely to their family crews when the task is complete. ECOS, now over 14,000 partners, receive the benefit of monthly lineman safety national webinars with relevant topics from communication, leadership, organization, training, and etc. Partner up by emailing safetytraining@bieremeters.com or go to electriccultureofsafety.com. Together, we are changing our electric culture of safety. A very innovative approach by Bierer Meters to getting information out. And I know, Jim, you and I have both presented at ECOS several times over the past couple of years. And, again, just goes to show what Bierer Meters is putting back into this industry that's been so good to them. Again, this ECOS that is led by Bierer Meters is at no cost to anyone. We all kind of give our time back to the industry to hopefully, give people the information and the support that they need to essentially make better decisions out there, right? And understand what they're dealing with in the work area. ECOS is a good deal. Jim, I want to thank you again. Before we do our closing remarks here, it's always a pleasure to, again, even, we work together, and I still, every time I listen or we have conversations, I pick up a little tidbit here and there. So, hopefully the others that are listening to this have the same ability to every time they listen to somebody talking about grounding and bonding and EPZ, they get a little more to put in their arsenal of knowledge to hopefully keep them safe and not become one of the statistics that we all, share and talk about that we ran into over the years because people just either didn't understand or were installing things. And unfortunately, we talk about it a lot, right? That people get injured or worse yet, get killed because of the protection that they think they're installing, the grounding that they think they're installing for their protection, and ends up, being the ammunition that led to their injuries or their fatalities. So hopefully we can continue to get that out there. In closing, the views and opinions shared in this podcast are the personal viewpoints of the participants and may not necessarily reflect the stance of the Institute for Safety Powerline Construction and its staff. It is highly advised to consult your company management before implementing any actions or policy changes. Please support the sponsors bringing this content to you. And for more episodes of ISPT Tailboard Talks, subscribe in your favorite podcatcher and be sure to leave a review. We'd love to hear from you. Again, questions can be sent to podcast@ispconline.com. Jim, thank you as always for your input. It's greatly appreciated and taking some time out of your day to share with us. Until next time on ISPC Tailboard Talks, I'm your host, Mark. Thanks again, Jim, and we will catch you all later. Be safe out there. Thanks all.
Y'all be careful out there.